and stochastic pseudo-monotone evolution equation. He has several works in this field. In particular, his recent work on the extension of Kruskal's theory to stochastic conservation law is highly cited. He has published more than 70 research publications, including several highly cited publications in prestigious journals. So today he is going to talk about Lewis-Stampake inequality. So let us welcome Professor Valen, and over to you now, Guy.
Thanks a lot for the introduction and the invitation to give a talk. So I need to share screen. Is it okay?
Yeah.
Yeah, perfect. So I'd like to talk about Lewis-Stampake inequalities today, and there will be few stochastic, and the main part is deterministic. So maybe it's better for the audience to be able to hear about both situations. First, I need to say that it's a work with my PhD student, Yassine Tarawi. He's a PhD student at the University of Pau and also in Algeria at the École Normale Supérieure de Cuba in Alger. So the main focus will be on obstacle problems. So, for example, if you think about here a membrane with a force, and here you've got a plate. So first, without the plate, so without the constraint, the plate will be the constraint, you have the solution to the problem, no problem. Here, if you add this constraint here, you've got a contact set with the plate, and in some sense, you will have the equation in some part where it's greater than the obstacle. And if you are in contact with the obstacle, then the solution is the value given by the obstacle. And here it's a classical Signorini problem with some ball elastic body on some plate. Another classical one is a Stefan problem about melting of ice, where you assume that in the ice part, U is equal to 0, U being the temperature, and outside, U is strictly positive, and then you will have the equation. So in general, the idea is that you've got a free set. Free means that you don't know where and when, if it's an evolution problem, where the set is. It's given by the value of U, and U is the solution you are looking for. So you don't know a priori what is that set. And on that set, it is the part where U is equal to the contact, to the obstacle. In general, the solution has to be greater than the obstacle. So outside this free set, it is another free set, of course. It is when U is greater than the obstacle, and you want the solution to be satisfied, or no, sorry, you want the problem, the equation to be satisfied in that part. You can claim, moreover, that in the free set, you've got an inequality. Usually, such situation is given by a penalization method. And to summarize, so you've got an inequality, two inequalities. First, for the problem, for the equation, that one is the inequality of the constraint, and then you claim that the product is equal to 0. This is formal because we don't know a priori the sets where such equality or inequality is old. So this inequality here is rather easy to obtain. This is the non-negativeness here. And Lewis-Stampake inequality is what about a control from above of the error in the satisfying the fact that the problem is not solved in some sense. I will be interested in three situations, two deterministic and one stochastic. In the elliptic case and the parabolic case, I will consider an operator A which is pseudo-monotone, and more or less it will be a Lorentz operator depending on U and grad U with the classical assumption. You need some coerciveness, some gross condition. You need some, but you will have, if A is a characteristic function, some continuity, so demi-continuity or some radial continuity. And in order to be in a situation where, without the constraint, you can solve the problem. For the stochastic case, pseudo-monotone operators are more difficult to deal with, and we will consider a monotone situation for the operator. So we will be, in general, in Sobolev space with an ultras for the Dirichlet problem, and we need some time for evolution problem to add L2 as an information in order to have the classical Gelfand triplet with L2. So what about the elliptic case? Consider a penalization problem. So you add this term to the operator. It's a, it's a monotone operator. You add to A, which is pseudo-monotone. It's of lower order with respect to the order of the operator. So it is still a pseudo-monotone operator. And you will have all the suitable assumptions to be able to apply a Bresis theorem on existence of a solution. The idea is to pass to the limit over epsilon, of course. Here, U doesn't satisfy a priori the obstacle problem, but imagine that you can pass to the limit, and if you can pass to the limit epsilon to 0, this means that this has to cancel at the limit, and so U has to be greater than psi at the limit. So it's the way you have the obstacle will be satisfied. So you can have a solution, and you need a priori estimates. Classical way to obtain a priori estimates is to be compatible with that term. So you use as a test function U minus the obstacle. You use the coerciveness, you need the gross assumptions. Assumptions on the obstacle, more or less it is in the same Sobolev space. So you have the boundedness of the sequence, and you can extract a subsequence going to some U. Here it's nonlinear. You have gross assumption, you can extract subsequence, and it is going to something you need to identify at the limit. And the aim of this penalization is to have that going to 0 when epsilon is going to 0 also. So at the limit, you satisfy the obstacle. Then you can use after U as a test function with U epsilon, and by suitable assumptions you've got on the problem, you can prove this inequality. A is pseudo-monotone, so with the weak convergent and this lim sup, you can identify the limit and also identify key as AU and this limit of AU epsilon, U epsilon. Then you are interested in mu epsilon being the future error in the problem and given by that. So it is negative part. For me, negative part is positive. So at the limit, I've got something which will be non-negative. Then I can pass to the limit because we're in the dual space, of course, because this is going to something in the dual space. So in fact, you can prove that you've got a mu, which is a non-negative element of the dual space, such that mu is a u minus f. And you can prove after, so this is okay. Then you can prove after that this product is equal to 0. And this is used, in fact, what you are doing is you use this equality, you use u epsilon minus psi as a test function, and you want to pass to the limit. Of course, you will have a term like that, and you can use this identification and prove this equality. In conclusion, you've got existence of a couple in V and the dual space satisfying the constraint with the non-negative. So mu is in fact the Lagrange multiplier associated to the constraint. So it is non-negative. You've got this and the product equal to 0. You can prove that this is more or less equivalent to the variational inequality you are used to. For example, if A is coercive and linear, it's the Stampaka theorem for variational inequality. So you can prove that this is equivalent. This is very classical. It's basics. You've got, so this part that is satisfied. The question is the Levi-Stampaka inequality. For that, you need an additional information. This information is that A minus F, so here it's A of the obstacle, has to be the difference of two non-negative elements of the dual space. So it's called a dual order assumption. And this is not all the dual. For Sobolev space, it's not a problem. U is U plus minus U minus. This decomposition holds in any Sobolev space, but in the dual of the Sobolev space, it is not the case. So in fact, elements satisfying such a decomposition, the set of such elements is strictly less than all the dual space. So you add this assumption. Let's check now the situation of the very classical situation if A is a strictly monotone operator, not pseudo-monotone anymore, but strictly monotone. In particular, you will have uniqueness of the solution. And you consider an auxiliary problem. This auxiliary problem, whose solution is V, is a problem of same type. Here you add H plus, remember it is this part, but instead of the constraint V greater than C, it will be V less than U. It is more or less the same, so you can practice the same by penalization, or just say that minus V is solution to the same type of problem. So you can solve the problem, you've got a solution, you've got a multiplier, and this multiplier lambda, because it is associated with this constraint, it's not non-negative, but it is non-positive. So as soon as you have this sign, then you can say that AV minus F is less than H plus, okay? It comes from this inequality. The steps after, are first to prove that V is greater than C. It can be done by some weak maximum principle techniques, very classical. And then you can use V as a test function in the problem in terms of U. And you can then compare the two problems, one of V, the other with U, and you can prove this inequality. Using the strictly monotone assumption, then U is V. That means that U satisfy this inequality. This is the Levi-Stampaka inequality. So that more or less the classical way obtained to prove Levi-Stampaka inequality around the school of José Francisco Rodrigues in Portugal, Lisbon, in situation of monotone operator. In situation of pseudo-monotone operator, it is not working the same. It's not possible to consider exactly the same technique because mainly of the lack of uniqueness of the solution. So the first idea is to try to check Levi-Stampaka inequality by assuming that H plus, which is a priori a non-negative element of V prime, okay? Now it's more regular, it's in L2. You consider the problem with whose solution is U epsilon, and you subtract by A psi. And you use after the information that A psi minus F has this decomposition H plus minus H minus. So you plug that inside this equality. So those two elements are non-negative, remember. I use this as a test function, and by sign information, that is non-positive, okay? And if I assume that this element, sorry, here, I'm here. If I assume that this element is L2, I can apply some Cauchy-Schwarz, Young's inequalities and control that element by the L2 norm of H plus. So this, of course, is the L2 norm of that element. That element is mu epsilon, the element I am interested in, because it will give me the information. It will give me information on the Lagrange multiplier. It is bounded in L2. I can pass to the limit up to a subsequence with a weak convergence, of course. And then I consider, I want to have more information, of course, on that element. I consider that it is H plus minus, or you know, classical plus minus in math. So H plus minus mu epsilon. And of course, this is controlled by the negative norm, because the negative part, because it is a minus sign, and by using suitable techniques of type weak maximum principle, I can prove, it's rather technical, that this element cancel at the limit over epsilon. Then at the limit, I've got Lewis-Tempelka inequality, AU minus F controlled by H plus, the one I was interested in. Of course, I am in the situation of a regular H plus. Now, I can imagine that I've got a sequence H plus N of L2 element and associated solutions. Of course, if I've got a sequence here, then I've got a sequence for Fn. Because of this situation, remember, if I have a modification of H plus, of course, then I want to keep the same obstacle, then F has to be changed with respect to what is changed in H plus. So I can solve the problem, and I've got this inequality. This is the Lewis-Tempelka inequality. Assume now that I'm able to have a sequence H plus N converging to H plus in V prime in the dual space, where remember that this element is non-negative element of the dual space. Then Lewis-Tempelka inequality is telling me that this inequality holds, and what is important here is that I can use the boundedness of that sequence and give an information of boundedness of that sequence in V prime. Because in the space V, as I told you, any U is as a decomposition U plus minus U minus. Else, it's not obvious for me that this inequality in any dual space gives a control of that element as a sequence, bounded sequence in the dual space. So I've got this boundedness. I can extract a subsequence. I keep the sign, and I can use the same trick, passing to the limit over n and having a solution to my problem. And this solution satisfies the Lewis-Tempelka inequality. So the idea is that in order to prove Lewis-Tempelka inequality, I first prove Lewis-Tempelka inequality in the context of regular data or regular data, and then I can use Lewis-Tempelka inequality as a technical tool to be able to prove Lewis-Tempelka inequality to the general case. So this is more or less what have been done by François Murat and Abdelhafid Bokran by using additional technical condition on the Lorentz operator, asking some Hölder continuity with respect to those parameters for a fixed vector. We extended this with Abdelhafid Bokran to the case of Lebesgue space with variable exponent. And more recently, with Yassine Tahawi, in the context of his PhD thesis, we could remove this technical assumption on Hölder continuity with respect to U. And the trick, it was a well-known trick, but we hadn't it in mind previously, is to modify the operator by asking A to have here the max of U psi. Of course, if you are in the situation of the penalization, U epsilon, you don't know if U epsilon is greater than psi, then it will be active. But at the limit, it won't be. So you converge to the solution. And here, what is important is that formally, if you are under the constraint, so you won't have A of x u grad u, but you will have A of x psi grad u. And then the operator will be formally monotone in the set where the constraint is not satisfied. It's formal, but technically that's the idea. I won't have any more problems with respect to u in the part where the constraint is not satisfied. We could also give some information on the bilateral problem. Now, the penalization for the parabolic case. We are more or less exactly in the same situation. Now, I need L2 to be added if P is too small in order to have the pivot space L2. And I consider this perturbation of A in order to be compatible with what I told you a few minutes. So I consider this problem with the penalization in the same. I can prove existence of a solution. You can use, for example, the recent book of Rougiscard on nonlinear problems. You have existence of solutions. So the uniqueness also is not required. And again, you want to pass to the limit with respect to the penalization, to respect to epsilon. For that, you need a priori estimates, and you use integration by part formulas in time and classical trick. And you have the classical a priori estimates you used to have in case of parabolic problem. The boundedness in L2 uniform in time, the boundedness in V with respect to LP, and this additional information coming from the penalization. So you can extract subsequences. One for U epsilon to some U will satisfy the constraint at the limit, and the convergence is weak in the LPV and weak star in L infinity L2. By gross assumption on the operator, you will have subsequence also for A epsilon U, A tilde U epsilon in the dual space. Now, the problem is to pass to the limit, but we need some compactness arguments. We need some information on the time derivative. The time derivative, usually for parabolic problem, you've got a priori estimates on the time derivative by using the problem, by using the equation. And using the equation, usually you've got that, and since it is bounded in the dual space, then it's okay for the time derivative. But you've got this additional term, the one coming from the penalization. And this a priori estimate is not enough. You haven't got here enough information in order to be able to say that this will be bounded in the dual space and have your compactness argument. So you need to work a little more, and you want to have more information on that term. You want to use it as a test function, classical trick, and for that, so you consider the problem with U epsilon, and you add the information coming from the obstacle. So here you will have minus psi, here you will have minus a psi, then you will have here on the right hand side the more or less the problem with using psi. Okay, and you will need additional information of order dual space type, so the decomposition H plus minus H minus. So you can replace, and if you have a look, here you can use the same tricks. Here you've got a sign information, the same information and minus H minus, this we don't mind about. So the problem is H plus with that element. Now, if you want to control the norms, then if you still keep here the brackets, so you will extract information here on the right hand side in terms of norm in V. Where can you have norm in V here? more or less nowhere, because here it will be an information in normal 2, and usually here you need the coercive assumption of Lex Milgram, for example, in order to absorb, but you won't have here. So it's not possible to go on without any information. The information you will use is the regularity of H plus. If H plus is more regular, then you will have an integral, and you can use the same argument here, Young's inequality, in order to control the term, and you will have this boundedness. Now, this boundedness is better than the former one, is compatible with the boundedness of the time derivative in the dual space, the one you were looking for. Now, you've got everything to be able to use your classical compactness argument for evolution problem. And so you've got here your compactness information. It will be used for this part here for U epsilon. Then after you go back to the equation and you need to prove that such an equality holds. And passing to the limit with respect to epsilon, you can use classical Minty trick, or you've got also here you will have an information of convergence in measure for the grad. So it's very classical for people working with Lorentz operator, and with here strictly monotone information with respect to psi. Remember that here we are working with a tilde. So if U epsilon is greater than psi, then U epsilon is kept. But if it is less, then it becomes psi. And this here say that U is less than psi. So you can pass to the limit, and you've got existence of a solution in the corresponding space. The constraint is satisfied. The Lagrange multiplier has the correct sign. The product is equal to 0, where here, remember, mu is more or less the default in the problem. Now, remember that we are interested in Lévy-Stampacchia inequality. So again, we say that mu epsilon is mu epsilon minus H plus H plus. And we need to prove that this goes to 0. So in the elliptic case, I told you it was technical. In that one, it is very technical. And for that, we had to consider a chain rule in time, so an integration by path formula in time for a parabolic problem, with rather more situation than the classical one of Atlukaus or Mignon-Berger. But we could manage to obtain and prove that this goes to 0. At the limit, then Lévy-Stampacchia inequality is satisfied. So control from by 0 and H plus for regular H plus. Now, same situation. We want to be able to pass from a regular H plus to H plus in the dual space, so the general situation. We can prove a result of density in some sense, of a non-negative element of LQ prime in the dual space, or the positive element of the dual space. So we are back to the existence of a sequence of approximation where for each n, the constraint is satisfied and the Lévy-Stampacchia inequality is satisfied. Again, this boundedness here by Hn plus, by assuming that Hn plus is converging in the dual space, can be used, and you will have the boundedness in the dual space of the sequence mu n. Then you will have again the boundedness of un. A priori estimates are kept. You've got this boundedness by the gross assumption on A. Now it's A and not A tilde anymore because the constraint is satisfied. And this additional information will give me the boundedness, as I told you, on the time derivative, and I can exactly copy paste what I did, but now with a general situation, and I've got a result. So just a few words on Lewis-Tempeke inequalities in evolution problem. As far as I know, one of the first results has been by Donati in 1982. And in the case of monotone operators, the trick was the one I told you in the introduction, using an auxiliary problem. And I think that situation with the pseudo-monotone operator had to wait 2018, where with Olivier Guibet, Abdelhafid Mokran, and Yassine Tahawi, we could prove existence of Lewis-Tempeke inequality for pseudo-monotone parabolic problem. And the technical information were first this trick of using A tilde at the place of A. So having something monotone and not pseudo-monotone formally where the constraint is not satisfied. We had to prove this embedding because we considered, I told you nothing about the obstacle. So think about obstacle in the same Sobolev space, or you can think about an obstacle in the Sobolev space W1P, but with non-negative values on the boundary. So it is not in the same in V. It is close to V, but not in V. So we have been interested in the situation where U is LP0T W1P, so not 0, so that the time derivative is in a dual with 0. So we are not in classical situation of a W0T, VV prime, and we have been interested in keeping the information of continuity in time in L2. And then we had to consider a general chain rule or integration by part formula in time, where psi is a very general function of time, of space, and u, more general than Alduca's and Minyu-Bomberger formula. No, I've got nothing else to tell you on that problem, and go on with the stochastic case. So the stochastic case, I told you now, it's a monotone operator, not a pseudo-monotone one. So keep in mind this trick of auxiliary problem. I will use this in a few minutes. Again, I'm in evolution problem, so I need to add the information of L2. Since a stochastic problem, you know that we have this stochastic integral here in the Ito sense. And for that, you need, if omega is the probability space where you will have the filtration and the Ito integral, you need additional measurability information with respect to the probability part. This additional information is the one denoted by capital P here, which is the predictable sigma field on the product omega time 0t. So everything has to be predictable because this is the measurability information I need in order to be able to put my process, my function, in the object, which is here the Ito integral. Okay, so everything is additionally predictable with the Lebesgue information, LP prime, V prime, and so on. I can prove the existence of a solution. So a solution here for epsilon positive is an element which is L2 in my probability space and continuous in time in L2. D here is the domain where I look for the spatial domain. And predictable with values in V. Here, this is the way you can understand the PDE, the stochastic PDE. So the time derivative is not active on U only, but U minus the noise term, the Ito integral of the reaction term, the term on the right of the equation. Here, the operator, and here the penalization. I can solve this problem. It's not an issue because A is monotone. I am adding here something which is monotone with all the compatible information, and I am in the context of the classical stochastic PDE framework, the one of Etienne Pardoux in his PhD thesis a long time ago, or the classical books on stochastic PDE with monotone operators. So I can solve the problem, and I want to pass the limit over epsilon, same thing. For that, I need a priori estimates, and a priori estimates is not testing the equation with u minus psi, but it's called Ito formula or Ito energy. And I've got exactly the same situation, unless the fact that I've got this additional variable in omega, small omega in omega, so the random part, and I need in the norms to have one more integral. This integral is the expectation. It is capital E here. So I've got exactly the same than in the parabolic case, and I've got the same conclusion, of course. I can extract subsequences with weak convergence. And one difference here is to pay attention is that if I want to use some Banach-Bourbaki theorem, then here it's not the classical measurability you will have, but the weak star measurability, the petit measurability, if I'm not wrong, because L infinity is not a separable space. So we need to pay attention to that. But if I am interested in saying that almost surely I am in an infinity, I don't mind in some sense about the measurability. Okay, so now I'm back to the information of dual order type. So the decomposition H plus minus H minus in the dual space, and I consider first the case of a regular H plus, exactly the same story. I want to have information on that element and pass to the limit with respect to u epsilon. So again, it's not testing the equation with this, but using an Ito formula. The small technical trick is that I'm not able to use directly Ito formula with a negative part because it's not regular enough. So I have a regularization of the negative part. I apply Ito formula, then pass to the limit of this regularization. And I can prove the boundedness in LQ prime by the same trick of Young's inequality. I can pass to the limit and have mu epsilon converging weakly to some mu that will be the Lagrange multiplier with the good sign. Here, because of a monotone operator, I will be able, I don't need compactness. So for those who knows compactness on a parabolic problem and we're afraid of that, no, I'm not using compactness. But since I have a monotone information, I'm able to prove that I've got a Cauchy sequence information in L2 and continuity in time in L2. Of course, this Cauchy information is good news, but not enough to be able to identify the limit in my operator. But I will have the almost everywhere convergence with respect to every variables, and I will be able to apply Minty trick at the end by monotone information and identify the limit. So at the end, I will have the existence of a solution to a problem with the good sign for the Lagrange multiplier. The constraint will be satisfied, and the idea of the obstacle problem, so the product equal to 0, will hold. Remember that here, the Lagrange multiplier is here, okay, in this formal writing of stochastic partial differential equation. I told you that this is the same than this writing here. If I have u minus the integral of that element, I put everything on the left-hand side, and I can have a classical time derivative and have back this without, of course, the penalization in that situation. Okay, I need now the second part of the so the more difficult part of Levi-Stampecker inequality, and I will use this trick classical trick for monotone operator. This auxiliary problem where I consider V with the control from above by U, solution to a problem where the source term is F plus H plus under that constraint, and I can prove the same way that I've got a Lagrange multiplier. Now this Lagrange multiplier is a non-positive because of the sign of the constraint. Here it's non-negative and that sign. Here it's, in fact, it's minus, okay, to get the solution. And here I got the multiplier. The steps are the same than the one I told you in the introduction. First, I need to prove that V is also greater than C. Then I can use the two problems with the same constraint greater than C for both U and V. Then apply a uniqueness method with, again, some Ito formula, Ito energy formula. And I can prove that U is equal to C. Sorry, U is equal to V, and since lambda here is non-positive, this gives me the second part of the Lewis-Tampere inequality. Here again, I am in the situation of a regular H plus. So for a regular H plus, I've got existence of couple solution U and the Lagrange multiplier solution to that inequality. Lewis-Tampere inequality. I consider now a sequence, Hn plus converging to H plus in the dual space. I've got the associated sequence of solution. Again, remember the decomposition of a dual order. And in the decomposition of a dual order, if I want to keep Psi as the constraint, then I have some kind of regularization of F by adding a regularization of H plus. I want to pass this limit. I use the Lewis-Tampere inequality in order to bring back on mu n abundantness in the dual space, and I can extract a sequence. I can prove after the same. I'm in the same situation, Cauchy sequence, Minte trick, and prove the Lewis-Tampere inequality for a general H plus. So again, the idea is first I prove Lewis-Tampere inequality in the situation of a regular H plus, and then I'm able, by using Lewis-Tampere inequality, to prove Lewis-Tampere inequality to general case. And also, it's a way to extend some result of existence of solution to variational inequalities, because Lewis-Tampere inequality can give me a more general way to obtain existence of solution to variational inequalities. Now, to finish, I'd like to say a few words about problems more or less solved with Yassin Tarawi, and also here it's a work with Imran on the stochastic case, but not with a parabolic operator, but with in situation of a hyperbolic operator, first order hyperbolic. So the constraint is to have U between 0 and 1. So it's rather technical and not that easy to work with. So you know that we are in situation of first order hyperbolic problem. So you need an entropy formulation. Here, the entropy formulation is given by this inequality. This inequality is with regular entropy because of Ito formula. I will have the second order derivative of the approximation of the absolute value function. So this is more or less classical now for stochastic first order conservation laws. So I cannot work with Kryskov entropies, but with a regularization. Here, so the time derivative, the flux part, here the source part, here it's the Lagrange multiplier. Here it's the reaction part, the stochastic reaction part, the additional term due to the Ito formula, and the initial condition. how to get such a result? It's done by artificial viscosity method. So you add minus delta U. So you are back to a parabolic problem. A parabolic problem with a constraint and the associated Lewis-Tampere inequality. It's possible thanks to the what I told you in the case of the stochastic study. And I need to pass those limits. So it's very technical, and we can prove existence uniqueness of solution in the case of constant constraints. So it's not obvious to if the constraint psi depend on t and x. For the moment, it's an open problem, but in case of constant, I think it is working. And the second extension is something with Olivier Guibet, who is specialist of L1 data. So we are back to the situation of the deterministic parabolic problem. We could solve with this information in the dual space. Now, what about information of L1 data for F and initial condition? So under some suitable conditions on P, so the power of the Sobolev space where we look for the solution, it's possible to prove the existence of a solution to the variational inequality, and adding more condition on P, we can have also the Lewis-Tampere inequality that is satisfied now in the sense of distribution, because in sense of duality with L1 data, it's meaningless. How to prove this? You can consider a truncature of the initial condition by some tk, and k goes to plus infinity for the approximation, and not truncature direct of f by tkf, because it's a problem with the dual part, but a tricky way to regularize f. We are back to the situation of the parabolic problem where we've got Lewis-Tampere inequality, and we can after pass to the limit and prove the well-posedness. But as I told you, there are several conditions on the power P, but it's classical for L1 data. Okay, so I think that it's more or less what I wanted to tell you, and maybe I can stop sharing the screen.
Okay, thank you, Guy, for this nice talk.
Yes, I can see that I have got several people.
Yeah,
it's questions to me. Or, sorry, but I had on this screen the conversions of U epsilon to U in terms of epsilon. So it was which part, the elliptic, parabolic, or stochastic when asking about the conversions of U epsilon?
Okay, we'll get back to that. So can you please check Q and A section, question and answer section, near the share screen option?
Excuse me, it's difficult to hear what you are telling me.
So you have share screen option, right? Next to that, you can see there is a question and answer section. There are lots of questions there.
Yeah, so there was some thing from Boris. Then after,
no, not that one.
Question.
Q and A.
So
it is written.
So there's. Can you see something about convergence of U epsilon to U in terms of epsilon?
No, that you are looking at chat, but not that one. There is a option Q and A. I don't know, in French it's written something else. So right of your share screen option.
Q and A. Okay. Oof. So fundamental difference between pseudo-monotone and monotone. Okay. So I don't know if it is the first. Yes, it's 11. So okay. So fundamental difference between pseudo-monotone and monotone. Imagine that you've got the Lorentz operator. So A minus div of A of something. A is a carotonoid function, and you've got A as a function of U and grad U. So when you've got U, usually it's pseudo-monotone. And when it's just monotone, you've got more or less only grad U. So think about the P-Laplace operator. But if in the P-Laplace operator, it is minus div of the grad U power P minus 2 grad U, then in front of the first grad U, you had a nonlinear function of U, for example, with a suitable control from above and strictly positive. So in fact, a pseudo-monotone operator can be seen as a monotone operator with what is called a strictly continuous operator, so something with the compactness argument you may have from a Sobolev space. So imagine something, a nonlinear operator of U, something like that. I don't know if I answered exactly the question. So it's a monotone operator with some U dependence, strongly continuous, so compatible with the compactness. It's why I was interested in Aubin-Lyon-Simon information for the parabolic case. Is it reasonable to consider obstacle problem with restriction on the derivative of function instead of the function itself? Yes, so it's so the obstacle on the grad. I'm afraid it will be more complicated. So there are some work I'm not really aware of, where you may have, for example, grad U in norm, Euclidean norm is less than 1 or something like that. If I'm not wrong to consider obstacle problem with restriction on derivative. So if the obstacle is on the derivative, so the grad instead of the function itself. So there exists, but it's not something I know, and it's not certainly compatible with what I'm doing there. So issues may be due to the penalization, because it's easy for me, the penalization, in some sense it's easy, because I'm acting the penalization so on U itself and not grad. So even for the first step, maybe the way to consider the penalization is more tricky in order to be able to apply classical results. So I will need monotone. Yes, why not? I don't know exactly. It's not something I've been interested in. So it's not maybe the answer you were looking for. In elliptic problem, you consider the linear perturbation, but for parabolic and stochastic nonlinear perturbation, that it with power Q. Okay. So the power Q is to be compatible with the a priori estimates. I will. So maybe more or less you could find the answer in the way I did in the proof. So I've got Young's inequalities in order to be able to absorb the part on the right hand side, but some term on the left hand side. So the way you consider the power in the penalization is there for technical reasons. I would be interested to have the suitable power in order to be able to apply my tricks with a regular H plus. That's the answer I can. So if you want additional information, of course, ask again the question. But more or less, it's a reason for technical. It's a suitable one. It's a suitable power to apply the techniques I'm interested in. For stochastic case, can one consider problem with other type of noise, say Levy noise? Marcus noise, I don't know, but why not Levy noise? Levy noise. So it can be checked, of course. Then I've got this this trick of Cauchy sequence in L2 omega and continuous in time. So for sure, this continuity, so means continuity of trajectories. With Levy noise, it's lost. Now, if instead of continuity, I've got L infinity in time, L2 in space, why not? I think that what I've been interested in is more the way to adapt monotone techniques compatible with penalization to the case of a noise. And I'm not sure, so, and if I have, of course, Ito formulas, then the type of noise, I don't remember if there's issues. So unless not to say stupid things like continuous trajectories, if just a Cadillac radar. But then after, maybe Levy noise, more or less, with suitable information, of course, it may work the same. I think so. For stochastic case, is it possible to consider random initial data? I'd like to say yes, if the initial data is in the F0 for the initial part of the filtration, why not? Mm-hmm. For elliptic case, is there any restriction on P? In what I did, no. 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 Restrictions on P, maybe in parabolic, when you look for some compactness. And in parabolic, restriction is just to add the L2 information in order to be able to have the pivot space. Else, as far as I remember, no restriction. Is a way to characterize element of the dual that admit positive and negative part decomposition. No, I don't know if there's an explicit way to know if an element is in the dual order. I don't know about that. I don't know. I don't know if there's some, probably, but I don't know. If you've got a solution, I'm interested in, but a priori, I don't know. The dual space decomposition. What are typical counterexamples? That's more or less the same type of question, no? If so, a typical counterexample. Boris, you should ask me the question last week in order to think about. I don't know. Typical counterexample. Because if I think about a regular element of the dual space in some Lebesgue space, then positive part, negative part is okay. If I think about measure, I can have decomposition, positive part minus negative part. Now, maybe with measure we need to take care, because with measure I can have positive part minus negative part, but are those two elements in the dual space? This I don't know. No, really, I don't know. Reformulation of delta prime. But in 1D, in the dual space, I need to be in the dual space also. Weaker reformulation of Levi-Stempel inequality in absence of decomposition. So for the second part of the question, weaker reformulation. First, I don't know exactly, but is Levi-Stempel, yes, Levi-Stempel inequality is also related to the fact that the decomposition exists, since the Levi-Stempel inequality I was interested in are controlled by H plus. So H plus has to exist. Okay. Now, the general question of Levi-Stempel inequality is: can I control from above the inequality? So it's a matter of inequality, and if it's a matter of inequality, I'm afraid that it's a matter of decomposition of positive part and negative part, and we are back to this kind of. So maybe I'd like to say no. Because I need this inequality to be possible. So more or less, I'm close to the inequality. So if about a counterexample, if the decomposition doesn't hold, in some sense, maybe I'm not able to control from above, and then Levi-Stempel inequality doesn't hold at the end. Boris is asking difficult questions, always.
Okay, thank you, Guy. So we invited Boris just because of this. So
yes.
The last question, Guy. So there was a question. Could you please explain this convergence of U epsilon to U for parabolic problem? So he mentioned for parabolic problem.
Okay, so what is exactly the question? Is the question about the quality of convergence? Because
yes. So how do you prove convergence of U epsilon to U?
Okay, so convergence of U epsilon to U is because I have the Aubin-Simon-Lyons theorem. So I have the boundedness of U epsilon in the dual space. Sorry, in LP 0T V prime. Okay. The gross condition on A is telling me that A of U epsilon is bounded in the dual space. Now I have this additional penalization. Without assuming the dual order information, I have not a control of the penalization compatible with the a priori estimate I am interested in. Now, assuming this additional information that the H plus is in some LQ prime, or I don't remember exactly, Lebesgue space, then I can improve the control of the penalization, and it will be in some Lebesgue space compatible with the fact that I will have the control in the dual space. So it's not very clear. I start again. I will, with this additional information, be able to control the penalization term in some LQ prime, such that LQ is in the range of the Sobolev embedding. So this LQ prime will be in the dual space LP prime 0TV prime. And then I can control the time derivative of U epsilon in LP prime 0TV prime. So I will have a control u in LP 0 TV and the time derivative of u in LP prime 0 TV prime, and I will have the Simon situation for compactness. So the convergence of u epsilon is in terms of compactness of Lyon-Saubin-Simon theorem of compactness. Is it
okay? Yeah. Thank you, Guy, for patiently answering all these questions.
There was something about Euler and Navier-Stokes. Maybe something exists, I don't know, but I'm not specialist of systems, so I'm not able to answer for that.
That's okay. That's okay. Thank you, Guy. So thank you for your nice talk, and thanks for the all answers. So before just closing this session, I just announce that our next speaker on Tuesday, next Tuesday, is Plum and Stefano from Purdue University. So because of this huge time difference, please remember the time. So I don't think that would be in the usual time, 3 p.m. Indian time. So do check our website for the details. So thank you, Guy, and thank you, everybody. So bye, take care.
Bye.